this anymore? I don't even know. This is, they auto-tune the fuck out of their voices. Definitely not. There you go. That's what we're talking about. Yes, you've officially entered old fart territory. When you talk about the good old days. Good old days. All right, shall we proceed? All right, so our goal now is to talk about, I've emphasized how there is this striking fact that's deeply related to locality and unitarity, that the way in which poles come together is captured by this shape. And now what we'd like to do, so this is a striking fact. It's not in the back of all the textbooks. It knows about factorization as well. And now this is a clue. Now this is our clue. We want to make this fact obvious. Okay? This has been a little bit hidden. Now we want to somehow find a question to ask in kinematic space that's going to bring this guy to light. All right? Now, before doing that, because we're going to spend most of the rest of this lecture talking about shapes, I want to tell you something about how the shapes are going to turn into the functions that are actually amplitudes. Okay? And so I could spend longer talking about this, but I'll talk about just enough so that we can proceed. And to tell you yet another fact about amplitudes, which is a certain hidden symmetry. Okay, the amplitudes have a certain hidden symmetry. That might surprise you. We're talking about a very dumb theory here. You would think there's no magic in this trace phi cube theory. And if you were to talk to me 5, 6 years ago, I would go around giving talks and saying, yes, Lagrangians are awesome for scalar theories. But when you have gluons and gravitons, and from the standard point of view, we need gauge redundancy and so on, that's where the on-shell way of thinking about things is better, blah, blah, blah. But for a phi cubed or phi to the 4th theory, nothing beats Feynman diagrams. Wrong. Okay? There is actually magic in the trace phi cube theory. And what I alluded to in the very beginning of the lecture that I'll talk about next week is the trace phi cube theory contains Yang-Mills theory inside it. That's the surprise. Okay? So there is actually magic in the trace phi cube theory, after all. I won't tell you about that today, but I will tell you what some of the magic is in the trace phi cube theory to begin with. Okay, so so this is just a few more clues of things that we're going to try and explain. But the first thing we're going to do is talk about scattering forms as opposed to amplitudes. All right? Now, here's just a very quick motivation. Yes? We're going to come back to this. Oh, big time. We're going to come back to this. I'm just giving you just a few more pieces of evidence of something going on that a picture is going to have to explain. Okay? So, yeah, all right. All right. So far we've been talking about scattering amplitudes, but I'm going to slightly upgrade the scattering amplitude to a certain differential form. Okay? And just to give you a motivation, we've seen that the poles of these guys matter a lot. Right? And we want to take poles, and we even said the word residue. But when you take a residue is not associated with a function. A residue is associated with a form. I can't take the residue of the function 1 over z. What does the residue mean, after all? At some level, you imagine doing a little contour integral, right? But I can't do a contour integral of 1 over z. I have to do a contour integral dz over z, right? So if I'm going to talk about contour integrals, I want to talk about forms and not functions. And something that should be clear ahead of time is we're going to be sort of looking for functions, okay, also functions, but functions and forms whose singularities are associated with shapes like that. Okay, and that's the sort of zeroth order idea that we've been seeing in this business, is that there are geometric shapes that emerge in kinematic space from the answer to certain combinatorial questions, and forms that have singularities associated with the boundaries of those shapes are where the amplitudes come from. All right? But I just wanted, this is a small digression, but I just want to give you some more things that, that the structure should be explaining. So instead of, let's say, at 4 points, instead of writing down the function 1 over x13 plus 1 over x24, which was our friend 1 over s plus 1 over t, writing it in many ways, now I'm going to write down something else. I'm going to write down a form. So instead of 1 over x13, what should I write? dx13 over x13, okay? And instead of 1 over x24, I'm going to write down dx24 over x24. Okay, so this has now gone from being a function on the space. So what is my kinematic space? It was the space of x13 and x24 in this problem. Now I have a 1 form on this space. Okay? No big deal. Now, what should I put here? A plus or a minus? And, well, here I'm going to tell you what we're going to do. I'll give you an a posteriori justification of it in a little bit. But we're actually going to put a minus here. All right? And one nice thing that happens if you have a minus there is that this form is actually only a function of the ratio x13 over x24. You see, if I put a minus sign there, this is just d log of x13 minus d log of x24, which is d log of x13 over x24. So it's only a function of this ratio. One way that you can say it is that it has what you can call a projective invariance. It's as if the kinematic variables actually live not in a capital N dimensional space, but in a capital N minus 1 dimensional projectivization of the space where you can rescale everybody by arbitrary scalar. So we have projective invariance under this sort of the variables x13, x24 scale to an arbitrary function of x13 and x24 times the 2 vector x13, x24. All right. Now, if I had a little bit longer, I would tell you, well, maybe I'll tell you very, very quickly. Okay? So this thing that we're doing here is very closely connected to the notion of something in this business that are called canonical forms. So this is just going to be a 5-minute digression on canonical forms, but this is just to give you an idea of how it is that you can associate forms with shapes. Okay, so that's the slightly cool thing. We're going to be talking about shapes. Amplitudes are functions. So how the heck are interesting functions going to be associated with shapes? Or there's this notion of a canonical form. Very loosely, the canonical form of a positive geometry. A positive geometry is just some space with boundaries of all possible codimension. Okay, so it could have an interior, codimension 1, codimension 2. Okay, so a square is a positive geometry. Any quadrilateral, any polygon, any polytope is a positive geometry because it has facets of all dimensionality. The interior of a circle is not, okay, because it has the inside, it has the perimeter as a boundary, but it doesn't have any points on it. Okay, so it needs to have boundaries of all possible codimension. In general, they can be curvy in what we'll be talking about today, and I'll hardly be explicitly talking about canonical forms, although they'll be in the background. We're only going to be dealing with flat things. Okay, so that's what a positive geometry is. For example, the simplest example of positive geometry is the inside of an interval. You have a one-dimensional space X, and you have an interval, let's say, between A and B. Right? That's the geometry. The interesting thing is that with these geometries are associated certain differential form, top dimensional differential form, which has the property that has logarithmic singularities. That means locally it looks like dx over x. The wedge product is a bunch of dx over x's. Okay? Locally it looks like the wedge product is a bunch of dx over x's. And it has those singularities on and only on the boundaries of the space. Okay, so somehow this differential form is completely determined once you give the geometry. So what is it in this example? In this example, the differential form would be, well, it has to have logarithmic singularities at x equals a, so it'd have dx over x minus a. It has to have singularities at x equals b, so it's dx over x minus b. And now, once again, what about the relative sign? It has to have a minus sign. Why does it have to have a minus sign? Because if it had any, so it needs this because, oh, sorry, and I should have said, and the residue of the canonical form on any facet should be the canonical form of that facet. So it's just recursively determined. So we go all the way down to points where the residue is just supposed to be 1, okay? So that's why they have the same, it's 1 plus or minus 1, but why is there a minus sign? If there's a plus sign, this thing would have a residue 1 here, and minus 2 at infinity. Right? This form would have a singularity at infinity. Well, that conflicts with the fact that the only places where it's supposed to have a singularity are at a and b and nowhere else. Okay? So that's what determines this minus sign. Okay, so that's very similar to what's going on here. Okay? Doesn't quite look like the same. This is a 1 form in a 2-dimensional space. This is a 1 form in a 1-dimensional space. Okay, but we'll see in a moment that these things are related. If I just quickly keep going, if I draw a triangle, let's say, so this would be, let's say, x equals 0, y equals 0, and this is x plus y equals 1. Okay, so I have the interior of this triangle. Then what is the canonical form for this guy? It's dx dy over x, y, 1 minus x minus y. Obviously, it should have the poles on every one of the boundaries, which it does do. Boy, that's bad grammar. Does do. Yes, it does. It does. It does. It's not do does. Okay? All right, so and now if we look at this and we now take the residue on x equals 0, what does it mean to take the residue? You literally imagine doing a little contour integral around dx over x, but it's really trivial. You just remove dx and set x equals 0. Then what am I left with? I'm left with dy over y 1 minus y, which is exactly the canonical form on that little interval, right, for y between 0 and 1. Okay, and you can check that all the other residues work as well, right? So this thing is the canonical form for the triangle. But what about this example now? Just to show you that shapes can determine interesting things. Interesting forms. Okay, so here's a quadrilateral. And let's say that the lines, they're just, the lines associated with these edges, let me just call it line 1, line 2, line 3, line 4. Each one of them is of a form ax plus by plus c, okay, for different values of a, b, and c. I'm not going to bother writing them down. So what is the form in this case? Well, it's dx dy over, well, clearly it has to have a pole on every one of these 4 lines, L1, L2, L3, L4, right? But now there's potentially trouble, because let's say I sit on the pole where L1 is 0. I'm taking a residue on the pole where L1 is 0. Well, this can have singularities, again, when either L2 is 0, L3 is 0, or L4 is 0. Okay, well, when L1 is 0, L4 is 0, that's good, that's that point. L3 is, L2 is 0 is okay, that's that point. But L3 is 0 is this point. That's not good, right? There's another bad point out here. Okay, so if I do nothing else, just this form with numerator 1, it's wrong. It does not only have singularities on and only on the boundaries of the quadrilateral. Okay, so what do I have to do? There has to be a numerator, n, and the numerator is exactly the equation for the line that passes through those 2 points in order to put a 0 there. Okay? Once I put a 0 there, then the rest works. Okay, I can't resist. In every talk of this subject I give, I get to be a Satanist. Okay? So what about the next example? This really freaks out people on the plane when you do it all day long, you know. Especially if you say, "Hail Satan," every now and then. Right? Okay, so here's my 5 gon. Again, if I put the 5 guys downstairs, L1 through L5, now there's 5 bad points, right? There are these 5 bad points. Okay, so the canonical form is still not done. I need to somehow put a 0 on top of those 5 bad points. Fortunately, if you remember your high school geometry, there's the unique conic that passes through 5 points. Okay, and that's the conic that appears upstairs to give you the canonical form. Okay? So these are simple examples where geometry completely determines a form, but you see kind of a sophisticated form, fancier and fancier expression. Right? This direct way of determining canonical forms is not trivial to do in general, and instead there's various simple theorems. Here's one of them. If you have a complicated positive geometry, if you triangulate the geometry, then the canonical form is equal to the sum of the canonical forms for the triangles. Okay? That's not 100% obvious, but it's true, so it's pretty obvious. So let's look at this quadrilateral example. Okay, so I can triangulate, for example, this like this. Now, I claim that if I take the canonical form for this triangle, 1, 2, 3, plus the canonical form for the triangle 1, 3, 4, it's going to give me the canonical form for the whole thing, 1, 2, 3, 4. Okay, now, why is that? Well, what do I have to check? I have to check that on the residues of this thing exactly are on and only on the boundaries of this space. What's the problem? The problem is obviously on this middle guy, which is not a boundary of the space, right? But the crucial point is that the residue on a facet has no memory of where it came from. It's just the form on the facet. It doesn't know that this 1, 3 came from a bigger polygon on one side or another polygon on the other side. The canonical form on 1, 3 is the same from both sides. And of course, the sign is just such that it cancels between the 2 of them. Okay? So that's why there's no singularities on the inside. Of course, meanwhile, everything else is guaranteed to work from the fact that we have the correct canonical forms for the other sides. Okay? So this is a technique for getting canonical forms from triangulations of your object into simpler pieces. All right, so just keep this in mind. This is a way that we can go from shapes to forms. All right, and the forms will be related to functions, which are the actual amplitudes in a moment. All right, but now let's close that as a digression, because the thing I've directly defined there is not yet what we're talking about. Is not yet a canonical form. Okay, the thing that I've just defined there is, the canonical forms are top-dimensional forms in the space where a shape lives. We don't see any shape here yet. Okay, I've just written in the space x13, x24, I've just written down this nice form. All right, so that's what we can call the scattering form. And actually, maybe since I'm here, just without too much fuss or muss, how do we get the scattering amplitude from the form? So here we have our space. We have this two-dimensional space, right? In this case, the space of x13 and x24. Right? So this is the two-dimensional space. That's our kinematic space for this problem. We have a one form that lives on this space, omega. Omega for n equals 4 is dx13 over x13 minus the x24 over x24. Now, how can you get a function out of a form? You have a one form. You could integrate. As soon as I said it, I realized I didn't want, that's exactly the answer I didn't want. Yeah. Okay, well, integrate. Where would you integrate it? Don't, I have to tell me where to start and end. I'm going to get a log when I integrate. Anyway, let's not integrate. Sorry? Well, I mean, you have a one form, right? You have a one form in a two-dimensional space. Mod squared is another good idea. Boy, these are all excellent ideas, which are not what I want. That's also a good idea, though. We'll come back to that idea. Maybe. Well, we have a one form. It's a two-dimensional space. So where do one forms want to live? One-dimensional space, right? So can we find a one-dimensional space in this two-dimensional space? Let's just draw a line, okay? I'm just going to draw a line. I'm going to draw the line x13 plus x24. It has to be symmetrical in 1, 3, and 2, 4. I don't know. So x13 plus x24 equals constant, okay? All right, so this is a line. I've sneakily drawn it so that C is positive. If C is negative, I draw it on this side. But anyway, for a future purpose, I've sneakily drawn it so that C is positive. Anyway, so I have this line. Now what happens when I take this form and I pull it back to this line? Right? What does pulling it back mean? That means I just evaluate everything on that line, right? So in particular, x24 equals C minus x13. So this becomes, let's say I write everything in terms of dx13. This becomes dx13, 1 over x13 plus 1 over x24. Of course, this x24 was equal to C minus x13. Okay? But you notice that when you pull back onto this one-dimensional line, when I pull back the form onto this one-dimensional line, I get the amplitude. I get the universal volume form, I factor that out, and what's left is the amplitude. The sign went away, what I'm left with is the amplitude. Notice something else which has happened. When I pull back to this line, what did this form become? It becomes the canonical form of this little interval. Okay? And remember, the little interval was what the isosahedron looked like when n equals 4. Okay, so this is a little clue about where we're going, that in kinematic space, there's just some big kinematic space, we're going to define a scattering form in the whole kinematic space, and I'll tell you something a little bit magical about it, this projective invariance. But we're going to find a plane to pull back the scattering form onto. And when we pull back onto that plane, we'll discover that it turns into the canonical form of an isosahedron. Okay, so the isosahedron will come to life, and the scattering form will be determined by being the canonical form of the isosahedron that comes to life on that kinematical space. Right? So this is just jumping ahead to what the picture is. We have the whole kinematic space. We're going to ask this question in kinematic space such that we get a form that's determined by the requirement that when we pull back under a certain subspace that I'll define in a moment, I get the canonical form of the isosahedron that comes to life on that subspace. And now you can also see why the minus sign was important here again, for the same reason as before. With that minus sign, I only have singularities on these two boundaries. With the plus sign or anything else, I would have singularities elsewhere. All right, but let's keep on going now. So if you tuned out of that, you can tune back in, because I'm going to tell you a little bit more about this form. So the magical projective invariance. So let's go to n equals 5 now. And now we have 1 over x13, 1 over x14, plus 1 over x14, x24, plus 1 over x24, x25, plus 1 over, these are the 5 terms, x25, x35, plus 1 over x35, x13. These are the 5 terms that we have for the triangulations. So the first one is 1, 3, 1, 4. The next one is 1, 4, 2, 4, and so on. Okay? So I've just drawn all the 5 triangulations. And we're going to make a form out of it. And I don't know the signs a priori. Okay. What we now want to ask is that this form is projectively invariant. Okay? That means that we want to ask that under x13, 1, 4, 2, 4, 2, 5, 3, 5 goes to alpha that might depend on all these variables times the same, that omega goes to omega. And now you can see that it's non-trivial that we can do it. At 4 points, we just have to choose a sign. We had 1 constraint, 1 sign, we could do it. At 5 points, already you're going to see that we're going to have more equations than unknowns. So it's not guaranteed that we can do it. And as we go to higher and higher points, the discrepancy is going to grow larger and larger and larger. All right? So it definitely is not obvious that you have enough freedom to just do this. It's a remarkable fact that it's possible to do it. All right? So, but let's just see already in this case where you're off by 1 equation. So under this shift, let's see, what does d log x do? So what does so d log of any xij goes to d log xij plus d log alpha, right? And so in general, at 5 points or any number of points above, what's going to happen is that we have these n minus 3 d logs, right? But under the projective variation, I'm going to have d alpha times a collection of things that have n minus 4 d logs in them, right? Because every term, I'm going to be able to take one of the dx's out and replace it by a d alpha. But there are many more n minus 4 tuples than there are n minus 3 tuples. Okay? So as I go to higher and higher n, the number of the number of signs that I have to control are the number of signs that go along with these n minus 3 tuples. But the number of terms whose coefficient has got to vanish starts growing much bigger than that. But let's just see explicitly in this case. Okay? So when I do this shift, I'm going to have d log. So without loss of generality, let's just call this first sign plus. Okay? So now I'm going to have d log alpha, right? And now it's got to be multiplied by various things, right? I could have d log alpha multiplied by d log x13, d log x14, etc. Okay? So let's see, what do I get for the coefficient of d log x13? Okay, for the coefficient of d log x13, well, I could get it from the d log alpha from here. So that's going to come in with plus 1. But where else can I get the d log x13? I can get it from here, right? And here it's going to come in with a minus 1. Is that clear? Because here I'm shifting. Here I'm getting d log x13, d log alpha from this guy. Here I'm getting from the d log x35, I'm getting d log alpha, d log x13. Okay, so if I pull out the d log alpha to be out front, then I guess, sorry, this one would have a minus sign. Okay, just because the wedge products are antisymmetric. And therefore, that tells me this guy has got to be there with a plus sign. All right? But now you see, now I'm stuck. Now I have to keep on going, and it's not guaranteed that it's going to work. Okay? Because then I have the coefficient of d log, then I check the coefficient of d log x14. That fixes this one. It turns out to be plus. Then the coefficient of d log x24 fixes this one, turns out to be plus. Then I'm just stuck, okay? That one just has to be plus, and there's one last one that just has to work, and I have no freedom for it to work. It turns out to work in this case. So here was very simple looking, and the answer was cyclically invariant, so you might not be that impressed, but it was not guaranteed by equation counting, okay? If you go to 6 points, the difference is more dramatic. If you go to 6 points, there are sort of 21, it's a number of edges, okay? There's 21 edges that have to work, whose coefficient has got to be 0, but I have 14 minus 1 for the overall sign, so I have 13 unknowns at my disposal. So I have 21 equations and 13 unknowns. They all have to be consistent, okay? So you can choose 13 of them, but then 8 of them just have to work. All right? And they do work. Okay? So this is an unobvious symmetry that this form has. It's a symmetry that's in many ways similar to the dual conformal invariance of n equals 4 super Yang-Mills, if you know about that. Okay? These are symmetries that tell you, I don't have time to talk about this in detail, but if you go off to infinity in certain directions in X space, the amplitude dies faster than you would naively think it would just by power counting, okay? Which is what happens under BCFW shift for gluon amplitudes and general supersymmetric shifts for supersymmetric amplitudes. The magic is that they vanish at infinity faster than you would naively think they would. And the same thing is true here as a consequence of the projective invariance. It's the projective invariance that tells you there's no singularities at infinity, and that absence of singularities at infinity tells you that the amplitudes actually die faster at infinity than you would naively think when you go off in certain directions. In the case of n equals 4 super Yang-Mills, the origin, the symmetry origin of that faster than expected fall off is a dual conformal invariance, because in the dual momentum space, infinity is not a special point. So you can't have any singularity there. And the analog here is this projective invariance. Okay? All right, so this is another fact about amplitudes. So now there's a few facts about them that we need to be able to show. One is that there is this projective invariance for these forms. And two is that it's possible to pull back the form to some subspace so that all the signs go away, and what you're left with is the amplitude, which is what we saw for n equals 4. Okay? So these are all things that we're now going to explain and understand. All right. Any questions now before we transition? Yes? It's labeled to? Oh, it's not. Oh, sorry. It's just that. Yeah. It's because one thing that the projective invariance tells you is that the form, despite appearances, is only a function of ratios of the x's. Okay, that's right. And because it's only a function of ratios on the x's, if we localize on any plane, it's going to have no singularities at infinity. Okay, that's the reason for it. And I should say something else, but thanks for saying that. The key thing about this projective invariance is that Feynman diagram by Feynman diagram, it is not obvious. Every diagram by itself has a singularity at infinity. Only the sum over all the diagrams together with the correct signs gives you the symmetry. Okay? And all of these things are going to be a consequence of the existence of the polytope, right? So that the polytope is going to explain all these things. Now, so what we're now going to do is give you the first kind of explanation for where this polytope comes from. It's actually the second explanation. The first explanation was a classic physicist screwing around, writing equations down way of doing things, which led to this particular realization of the icosahedron. This is what it looks like for the same 6-particle scattering. If you look at it closely, you'll see it's combinatorially looks exactly like this picture. It still has 6 pentagonal faces, 3 square faces, exactly the same pattern of how everything comes together. But it's a very particular looking realization. It's drawn a little bit badly because it has a lot of parallel sides. It's a very particular realization. So this is what we ran into with some friends back in 2017. Some mathematicians are now calling it the ABHY icosahedron. Okay? And so it's a particular realization of the associahedron. And so I'm not going to tell you the very original motivations, but I'm going to tell you somewhat more rational ones, okay? Now, so for the rest, next however long we're going to do this, we're just going to play, right? We're going to play in kinematic space. And at various points, I'm going to pull things out of nowhere. Not that nowhere. We'll do very natural-looking things. We'll play with wave equations. We'll do but we're playing. You should just keep in mind we're playing. This is not supposed to feel super systematic or it's some first principles derivation or anything like that, okay? So just have that relax, right? So tomorrow, we'll talk about 100% conceptual origin of these things with zero choices. You begin, you do something, you follow, every one step follows the next, nothing you can do, and you run into these objects. And not only at tree level, at all loop orders, beyond the planar limit, blah, blah, blah. All right, so that's what we'll talk about tomorrow. And I think we'll be able to get through at least the proper introduction to that tomorrow. So if you care to follow the developments in these subjects, you will be able to do so after tomorrow. But for the rest of today, I just want to give you a flavor of where these things can come from, so that when we get slightly more abstract tomorrow, you'll know why it's worth hanging on and seeing where these things actually come from. Okay? All right. So, but again, feel free to interrupt, ask any questions, and let's proceed. So, so for the umpteenth time, we're going to write our kinematic space. Our kinematic space is chords of the polygon xij, where I have to remember that the xii plus 1s are 0. Right? These are my on-shell guys. Everyone else. All right, but I'm still not super explicit enough yet. I'm a very dumb guy, right? I just want to keep track of all the variables. I just want to see all the variables. All right, let's just write all the variables down, shall we? All right, we're just going to write them down. Now, if someone told you to keep track of the variables, x1, 2, x1, 3, x1, 4, x2, 3, x2, 4, x2, 5, how would you keep track of them? You'd probably draw them on a little grid, right? So we're going to draw them on a grid. All right? Only thing is, I'm going to draw, very naively, you would have done it like 1, 2, maybe 1, 3, 1, 4, right? Maybe 2, 3, 2, 4, 2, 5. Maybe you'd have done something like this. I'm going to tilt it by 45 degrees. You'll see why I'm tilting it by 45 degrees in a second. I don't have to, but it'll make it easier. So let's, yeah. Let me. Okay, so I'm going to draw it like this. So here's 1, 2. Here's 1, 3. Here's 1, 4. 1, 5. Here's a case of 6 particles scattered. Sorry, 1, 2, 1, 3, 4, 1, 5, 1, 6. Okay, it's going to be 2, 3, 2, 4, 2, 5, 2, 6. Okay. And then this would be 2, 1. This is 3, 4, 3, 5, 3, 6, 3, 1, 3, 2, and so on. Okay? And I can keep on going in this direction as well. The central challenge in this subject is I can't draw 45-degree lines. Okay? So I'm going to crap out. This is 3, 4, 2, 4, 1, 4. And this is going to be 6, 4. And this would be 1, 2. This would be 6, 1. Oops. What did I do? Oh, yeah, that's fine. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and so on. All right? Okay, so is it clear? I've just drawn all of the ij's in the most obvious way on a grid. Let me call this direction, I'm just going to give these directions names. So this is a little bit of foreshadowing. We're going to call this a kinematic spacetime. 1 plus 1-dimensional spacetime. This spacetime has absolutely nothing to do with ordinary spacetime. 0, okay? But this is an interesting kind of emergent 2-dimensional, 1 plus 1-dimensional structure in the kinematical space. I have not told you yet where this 1 plus 1-dimensional is. We'll do that in 3 minutes, okay? But first, let me just justify why I drew it in this 45-degree lines. I'm just trying to distinguish the guys that are on shell from the guys that are genuinely dynamical variables. So all the things on the boundary here are not really variables. They're just fixed to 0 by the on-shell constraints. So that's why I drew it like this. Had I drawn it like a normal grid, oriented normally, then these boundaries would have been 45-degree lines, okay? No big deal. So I've just rotated it so the boundaries are vertical. Okay? So these are just words for now, but I'm going to call this the space direction and this the time direction in the kinematical space-time. Okay? Just words for now. So you'll notice something, that here I have 1, 3, and up here I have 3, 1. Remember, ij and ji are the same thing, all right? So we have this infinite strip that has the obvious sort of cyclic symmetry of the problem, right? In this case, rotating everything over. But it actually has an extra Mobius invariance, right? It has the identification between xt here, and if this separation I just call 1, and 1 minus x, 1 plus t here. These points are identified with each other, right? So that's an interesting little topological feature of just this labeling of the kinematic data, all right? Now, why do I say the words kinematic spacetime? Because there's something cool here. Remember, something matters a lot in our picture if chords cross or not. Right? If we have crossing chords, we're supposed to care about that. Right? So you can ask, if you have ij and kl, if these chords cross, what does that mean for how the chords appear in this strip? Okay? And the answer is very beautiful. If ij and kl cross, then ij and kl down here actually form the past and future corners of a causal diamond that fits inside the kinematic spacetime. Okay? So if this is ij, this is kl, then this would be ik, and this would be jl. So if all 4 of these points, in other words, if I look at the 45-degree lines that go out of ij, and those go back from kl, and if they fit, if they intersect so that all the points live inside my strip, then and only then are ij and kl crossing chords. Isn't that cool? Okay? So somehow the notion of crossing is equivalent to a notion of causality in the label space. Remember I was telling you, you think there's nothing going on in these spaces, and you just start drawing them, and then something starts coming out. Okay, so we've done absolutely nothing other than record the stupid variables. Okay, but just recording the variables, then there's something interesting happens. That whether or not things cross is equivalent to some kind of causal structure on this space. All right, so let's see that in action here. For example, on our 6-gon, this is a 6-gon. let's see, for example, 1, 4, and 2, 5. Indeed, they're the Paston. That's definitely associated with something that has a causal diamond. Yes, indeed, 1, 4, and 2, 5 cross. Okay, but 2, 5 and 3, 5. Nuh-uh. 2, 5, and 3, 5 are not the Paston future corners of a causal diamond that fits, right? They're not separated. They're not the Paston future corners, right? So the ones that are compatible are either space-like separated, or they're so far time-like separated that the backwards and forward light cones from them can't reach each other. Okay, and that corresponds to the two different ways that things could be compatible. Either one contained in the other, or the two sort of disjoint from each other. Okay, so those are the sort of two patterns in which things can actually be compatible with each other. Okay, but if they're incompatible, they're the past and future corners of a causal diamond that fits in the space-time. All right, so keep that in mind, and so that's the reason for the word sort of kinematic space-time. There's a useful, emergent causal structure in the space of labels, right? In the space of labels, it's useful to think about a kind of a 1 + 1 dimensional space-time structure on them. All right, now a little bit more. We want to talk about a kinematic space-time. So remember, because the variables x, I, j, and ji are identified with each other, of course, this is an infinite picture, so all the variables are copied infinitely often, right? So one thing that would be useful to do is to find a chunk in this picture where every variable occurs once and only once. Okay? So that's just another, we're just trying to describe our kinematic space as concretely as we can. Okay, so this way it's still redundant, and there's many ways of doing it. There isn't a unique way of doing it, but here's one that we're going to use for the rest of this talk. Very simple and nice one. The inside of this right triangle. Okay. So let's just look at what all the variables are. How many do we have? We have 1, 3, 1, 4, 1, 5, 2, 4, 2, 5, 2, 6, 3, 5, 3, 6, and 4, 6. Those are 9 variables there, right? That's the correct number of variables. And you'll see that, for example, I have 1, 3, but not 3, 1. Right? I'm only keeping one copy of everybody. I have 1, 5, but not 5, 1, which is up there somewhere. I have 3, 6, but not 6, 3. Okay? All I've done is keep one copy of all the variables. There are many other ways of doing it, but essentially you have to take a chunk out of this. You make a choice. You have to make a choice. You take a chunk out of this kinematic space-time. It's very amusing that this chunk out of the kinematic space-time looks a lot like the Penrose diagram for scattering amplitudes in flat space. Okay, that's kind of fun, and we're going to take quite a bit of advantage of this point of view in a moment. All right, so is it clear what we're doing? We've just labeled kinematic space, right? And we can do it with this right triangle for any n. Okay, so that's trivial to see. That right triangle captures all the variables once and only once. So now we're really done with the setup, okay? This is our kinematic space, this right triangle, right? And now, in this space, we have to find a question that for some reason makes it obvious that there is a pattern of poles that comes together that's polytopal, that gives us the isosahedron, and that has factorization, so that if you go on the facet of that polytope, it'll factorize into the product of lower polytopes of the same type. That's what we're looking for. Okay? So does anyone have any ideas? Those of you who haven't read the paper, so aren't that cheating. Yes, any wrong answer is fine. Yes, yes. I'm trying to get you into the spirit. Yeah. So here you are. This is your canvas. This is your playground. 1 + 1 dimensions. This is your kinematic space. Go. Your hologram for flat space awaits you. Right? In this space, you're going to ask a question. You have to bring the isosahedron to life. when you run into 1 plus 1, when do you first run into 1 plus 1 dimensions? When you're a kid. What do you do in 1 plus 1 dimensions? Huh? Wow. Penrose diagram, you're a pretty fancy kid. I want to go to your school. Huh? Some trajectory, okay. Let's see. Let's see. Okay, what's the simplest equation that you could write in 1 plus 1 dimensions? If someone says the Dirac equation, I'll kill you. Oh, that sounds nice. That sounds nice. The Klein-Gordon equation. Does that have a name for kids in high school? Wave equation. Okay, wave equation. That's nice. All right. So, all right. That's what we're going to do. We're going to just write down the wave equation in this 1 plus 1 dimensional space. Now, let's actually stop for a second and, well, let me motivate it. Okay. So, before doing that, let's just remember some facts about the wave equation in 1 plus 1 dimensions that we sometimes don't emphasize. You know, you're used in school when you run into it in high school or whatever to think about the wave equation in very Newtonian terms. Like someone gives you the value of the string x and x dot, as usual, right? You're given x and x dot on a Cauchy surface and you evolve into the future. There's a much cooler aspect of the wave equation, a more Lorentzian aspect, which we don't emphasize, which is that if you give the data on a null surface, just the data suffices, no dots, okay? You just give that's the globally hyperbolic statement, yes, okay? So, in fact, if someone hands you the wave equation in this space, right, then if I give you the initial data here, and boundary conditions on here, let's say, then I can solve for x everywhere inside. Now here's actually the fast way to see all of these things, which is to remember the Gauss's law. So what is the Gauss law for the wave equation? Right? So remember, what is the wave equation itself? It says that you have du dv of like phi, or let me call it capital X, because that's what I'm going to call it, equals 0. Right? So where u and v are these directions. Right? I'm talking in the continuum for the moment. Right? So the wave equation says du dv x equals 0. So what's the Gauss's law? Oh, I'm sorry. And if you have a current, we're going to talk about a source, so I'm going to call the source C. Okay? So du dv x equals C. So what is the Gauss law? The Gauss law is very beautiful. It says you take any causal diamond, right? The Gauss law says that if this is past, future, left, right, the Gauss law says that x past plus x future minus x left minus x right equals the total charge C that's contained, integrated in this diamond. Okay? Is that clear to you guys? If not, just imagine making this diamond arbitrarily tiny. In the limit where this diamond becomes tiny, what does this combination turn into? Exactly du dv, right? That's exactly the double derivative of du dv. So this is the integrated form of the wave equation, and it's the super fastest way to remember how to solve the wave equation in 1 plus 1 dimensions. Okay? All right? So now, because of this, it's clear that if you give me, let's say, x on this past surface, then any point x here, how do I solve for it? Well, I just plonk down this little causal diamond, right? So then I get this plus this minus that equals that, okay? And I can solve for every point inside if I've specified what x is here, as well as these boundary conditions there and at the tip. All right? Is that clear? So it's very cool that when you're solving the wave equation, it's exactly like the scattering amplitude problem. You just give the amplitude in the past, and you determine the future. No x and x dot, okay? So that's the, just x is enough. Okay? So far, so good? Now, all we're going to do is do the obvious discrete analog of that, right? We don't have the whole continuum space. We have a kind of a mesh. But we're essentially just going to write down exactly the wave equation, except instead of writing the continuum wave equation, we're just going to write down these Gauss's law equations, right? We're going to write down these little Gauss's law equations for all the small meshes in this problem. Okay, so this is our version of dynamics. So we finally defined our kinematic space after all the song and dance. And now we're going to ask a dynamical question in this kinematic space. And our dynamical question is going to be the wave equation. We're just going to solve the wave equation in this kinematic space. Okay, at many points here you could be complaining, why did you do this, why did you do that? And so that's what I told you, so relax, right? So this is just to show you what sorts of things to expect in this way of thinking about things. And tomorrow we'll start from absolute scratch. And if you're unhappy with all this artisanal mucking around today, you'll be happier tomorrow. But this gives you, I think, a very good intuitive idea of the kind of things that are going to be involved in this way of thinking about things. All right, so is it clear what we're doing then? Let me draw a smaller example. Actually, let me start with the smallest example. All right. So our space is, what is our space? Is labeled by 1, 3, and 2, 4. Why did I change colors constantly? All right, sorry. So our dynamical variables are 1, 3, and 2, 4. Right? So what we're saying is that there is this space, this two-dimensional space of 1, 3, and 2, 4. But we're going to restrict ourselves to a subspace of this two-dimensional space that solves the wave equation. Right? And what is the wave equation here? Is just going to be x13 plus x24 minus x24, x23 minus x14 is equal to the c, right? And just by convention, I'm always going to label the c for this little mesh by its bottom passed corner. So this one I'm going to call c13. In this case, it just so happens, of course, x23 is equal to 0, and x14 equals 0, just sort of accidentally, because this is such a small problem. These are at the boundaries. So I'm just left with x13 plus x24 is equal to c13. You can think of this as solving for x24 in terms of the initial data, which is x13. Or I could have done it backwards, of course, solving x13 in terms of the final data, which is x24. Of course, this equation might look a little bit familiar from our past mucking around at 4 points. But let's just say now that further restriction we're going to make. So we're going to ask for the x to solve the wave equation. But so this is our dynamics. Something else which has come up in this kind of approach to amplitudes for the past 10 years or so is, at an appropriate point, the injection of the word positivity. Okay? So this is the point where we're going to say the word positivity. We're going to want x's to be positive, all the x's to be positive, greater than or equal to 0, and these c's to be positive. Okay? So what that means is that in order for all of this, so imagine the c's are fixed. Imagine the c's are just some fixed positive numbers. We want to look at in the space of the initial data, in this case in the space of x13, what is the part of that space of initial data where all the x's are still positive on the support of the wave equation, right? So what does it look like in this case? So let's say I plot things as a function of x13. Okay, so I'm asking that x13 itself is positive. So I have to be, if here's the origin, x13, I have to be on this side, right? But I also want that x24, which is equal to c minus x13, I want this also to be positive. Okay, so this puts another inequality. Because c is positive, the inequality is on this side, and that forces me to be over there. This is x24. This is x13 being positive. This is x24 being positive. And so the two of them together imply, in my x13 space, that I can't live in an arbitrarily place. I have to live on the inside of this interval. Okay? All right, so that example was a little bit small. Let's go to the next example. Next example is a little bit more fun. Okay, so let's do 5 points. Well, you see, from this point of view, as we keep going, the locality and unitary emerge from positivity. You can always keep pushing the why question back. Why positivity? Okay, but I think even if it's not, I'm not giving you any kind of formal proof or statement or anything like that. I hope you get the feeling that we're not cheating here. We're not sort of secretly looking at, oh, what is it going to take to get the answer to look like Feynman diagrams, and then we're going to build it in, right? This is some question that clearly it's kind of pulled out of somewhere, but it's a natural question. It's not a crazy question you ask in this space. And the answer is going to give us locality and a unitarity. Okay, so, and again, tomorrow we'll understand much more systematically why this happens, but this is to give you the sort of flavor of what's going on. So indeed, it's definitely not obviously locality and unitarity imply this positivity. It's kind of the other way, right? You take this shape, these rules, and they're going to give us, and that's also why I was emphasizing, by the way, the fact that the pole structure is polytopal is more than locality and unitarity. It's something even extra. It contains locality and unitarity, but it's even more, right? It knows about projective invariance. It knows about other things that we didn't know about just from locality and unitarity. It really goes the other way. It's not a marriage of equals. So this other picture knows more. The problem is we need to understand where these pictures come from systematically for any theory. That's the big challenge in this subject. So far it's this theory, this kind of observation, that playing around. But when you find them locally, it's clear who's on top. So that's yeah. Okay. So let's do the next example. All right, I'm really going to write out all the equations. Okay, so here my variables are 1, 3. The 5 variables are 1, 3, 1, 4, 1, 5. 2, 4, 2, 5, 3, 5. These are my 5 variables. And what are my 3 equations? For this mesh, I have x13 plus x24 minus x14 minus this guy, but that guy is 0. So minus 0 is equal to C13. From this guy, I have x14 plus plus x25 minus x24 minus 0 equals C14. And then finally, from this guy, I have x24 plus x35 minus x25 minus 0 equals C24. So these are three equations that I can think of as three equations for the three unknowns, 2, 4, 2, 5, and 3, 5, to be determined in terms of the initial data, 1, 3, and 1, 4. Okay, so my initial, yes? Yeah, it's not supposed to be a branch cut. I'm just drawing it to say that in x13 space, I'm only restricted to lie inside this interval. Sorry, yeah. Yes, sorry, I didn't mean to, yes. I didn't mean to make it look like a branch cut. It won't look like a branch cut when I draw it now. All right. So these are three equations that I can use to solve for 2, 4, 2, 5, and 3, 5 in terms of the other guys. Let me just solve them for you. So we get that x24, and actually, just a little trick, you don't have to solve the three equations and three unknowns. This is just solving the wave equation, so we can directly use the Gauss's law, okay? So for example, x24 is going to be just solved using this little Gauss's law. So x24 plus x13 minus x14, right? Just that. Well, that happens to be the top formula anyway, but x24 is equal to C13 plus x14 minus x13. But x25 is equal to, you see from here, I use this Gauss's law. So 2,5 plus 1,3 minus 2,3 minus 1,5. But these two are 0. So 2,3, 2,5 plus 1,3 minus C13 minus C14 equals 0. So x25 is equal to C13 plus C14 minus x13. Of course, you can get this. That's the point of Gauss's law, is that you can get this equation by the sum of the equations for this mesh and that mesh, right? That's our usual like Stokes theorem-like argument. All right, so, but I can also, instead of starting from the equations and taking linear combinations, I can just stare at the picture and just draw the Gauss's law to begin with, okay? And finally, I have x35. x35 is equal to C14 plus C24 minus x14. All right. Now, same deal. Now I have to demand the C's are positive and all the X's are positive. And that is going to force, in my space of initial data, x13 and x14, I have to live inside some region. All right, so what does this region look like? Okay, so let's say here is 1,3 and here is 1,4. Well, obviously, 1,3 has got to be positive and 1,4 has got to be positive, so I'm definitely living in this upper quadrant, right? Okay, but where is x24 equals 0? x24 is C13 plus x14 minus x13. So the line where x24 equals 0, so let me just label this. So this line down here is where x14 is going to 0. That's that line. Here is where x13 is going to 0. Now, what about where x24 is going to 0? Well, that looks like this, right? And what is this intercept? Here is C13. All right. So this line is where x24 goes to 0. And x24 bigger than 0 is where? It's on this side. Okay? So I have to be on this side here, this side there, this side there. Now what about x25? Well, x25 is some constant minus x13. So that's a parallel line like this. Note, crucially, the C's are all positive. Because the C's are all positive, this C13 plus C14 is further along than C13 because C14 is positive. So this next line is going to be over here. Okay, so that's going to be where x25 goes to 0. Okay, what about on this side, x35? x35 is C14 plus C24 minus x14. And once again, because the C's are positive, this is going to be bigger than C14, which means that where this is going to be above that line. So this is going to be where x35 goes to 0. And so I got my pentagon. Right? Okay? Now, you do the same thing for n equals 6. You can do it on Mathematica right now, anyone who wants to do it. It's very fast. Just use region plot 3D. All right? And you just do exactly the same thing. You now have 6 equations. You use it to solve for the 6 other x's in terms of the initial guys. You plot the regions where they're all positive. You choose some values for the c's, and you get that 3-dimensional shape. Okay? Okay? So the icosahedron is the answer to this question. Solution of wave equation in kinematic space-time with positivity. All right? If you want the one-sentence summary, we went to kinematic space, we defined it carefully, we saw it has this little causal structure, we solved the wave equation, and we said the word positivity. And what comes out is the icosahedron. Okay? Now, why? So let me now conceptually show why. In other words, what I now want to do is show what is special. Why is this the icosahedron? Well, first, let's talk about locality and then unitarity. So I want to now show how positivity plus the wave equation implies locality. I mean, here we just saw it in examples. And unitarity, but now I want to show explicitly why it does so. So first, locality. Locality, remember, was a statement that the only poles should correspond to non-crossing chords. What that means is that there should be no facet of the association. It should be impossible, remember, to hit a pole, we want to send a given x to 0. Maybe I should have said that from the very beginning. What was the motivation for saying the x's are positive? I didn't say that. I'm sorry. I should have said that early on. It was not just saying the word positivity. It's because we know in the back of our minds that we want some kind of poles or something to happen near x equals 0. So x equals 0 should be special. And we're going to make x equals 0 special by making it a boundary of the space. Okay, so that's the main idea, and that's what we saw earlier, this notion of canonical form and so on, that the functions were associated with putting singularities on the boundary of the space. So that's why we ask for the x's to be positive, because we want x equals 0 to correspond to poles of whatever function we're going to talk about at the end. Okay? But now that we know that, what does locality mean then? Locality means that if you have 2 facets of the icosahedron, this corresponds to some x, some chord ij, this to another chord kl. If ij and kl are incompatible, if they cross, then those 2 facets should not be able to cross. They shouldn't meet in the icosahedron. They should be kept apart. Right? And again, that's what was special about our pentagon, right? 1, 3 and 2, 5 cross. And 1, 3 and 2, 5 are kept apart. They don't meet. 2, 4 and 1, 3 cross. They're kept apart. They don't meet. All the ones that do meet are the ones that are allowed to meet, that are compatible. Okay, the ones that cross are kept apart from each other. Is that clear? All right, so the first thing that we want to understand is why are the only poles that we see, why do they correspond to non-crossing chords? Okay, well, it's incredibly simple. Remember, as a consequence of this Gauss's law, for any causal diamond, past, future, left, right, we have the formula x past plus x future minus x left minus x right equals C, where C is the total sum of all the meshes. Since all the C's are positive, this is a positive number, right? Remember, on the isosahedron, we're asking for all these x's to be positive, or at most 0 when they hit a boundary. But I can't put both the past and the future to 0. If I do, the sum of two negative numbers would add up to a positive number, which is impossible. Okay? So positivity guarantees that facets that correspond to crossing chords don't meet in the isosahedron. That's locality. Locality from positivity. Is that clear? All right, so that's locality from positivity. Now, factorization. This is a fun argument. So let's review so far what's obvious. What's obvious ahead of time is that from this picture we're getting a polytope by construction, right? We ask for a bunch of things to be positive. That means that we're living on some positive orthant together with a lot of other planes being positive. So we're manifestly building something which is a polytope, and whose facets are associated with chords of the polygon. Okay? Now we've learned that crossing chords can never meet, that the facets corresponding to crossing chords can never meet. The final thing we've got to show is that when you go on a facet, what it looks like is a direct product of smaller objects of the same type. That's the last thing that we have to show. If we show that, we're done. Then we've manifested everything. We've manifested that we have a polytope with correct properties to be local and unitary, right? Okay? Okay. So to do this, just for simplicity, just so I don't draw a mesh, which will look ugly, I'm just going to phrase the argument as if it was in a continuum. But just imagine putting a very fine mesh on top of everything that I'm saying. It doesn't matter. Okay. This is a fun argument. So let's say we have this picture, and I'm going to a boundary. So going to a boundary means that there is some point here, x star, and I'm putting x star to 0 there, right? And generically, x star is positive, but I'm putting x star to 0 there. Okay? Now I want to know what happens to the shape of my space, right? I have a space which is defined in terms of initial data here. So when I go to the boundary, I'm somehow moving the initial data around to allow this x star to go to 0. And then I just want to see what does it look like there, right, in that neighborhood. Well, a very natural thing to wonder is, what are the other x stars? What other x's can I now set to 0 in this picture? Okay? Well, let's shoot out the obvious 45-degree light rays. Boy, not great. All right? Then I hope it's clear that all the x's that are in here and are in there can never be set to 0. Right? Why? Because they're either, together with x star, they're either the past or the future corner of a causal diamond that fits inside the space. And those are exactly the guys that are incompatible, right? So none of these variables can ever be set to 0. Furthermore, it's trivial to see from Gauss's law that you can, if you wanted to know what these variables were, you could completely reconstruct the value of these variables given the knowledge of the x's just everywhere here. Okay, like you can reconstruct everything in here, given the knowledge there and there by Gauss's law, given the knowledge there and there by Gauss's law. Okay, so you can reconstruct everything. You don't need these inside of the rectangles at all for any purpose. You can totally reconstruct everything about them by knowledge of things on the boundaries of the pictures that I drew. And so that means that every point in this space is in one-to-one correspondence with the point in a different problem. In a different problem where you take this little triangle, let me just draw it there, and you take this rectangular region and you scrunch it. So you take this whole triangle and you move it down, and you take this triangle and you move it up. So if you do that, you're left with something that looks like that. Everything that was in here is now been scrunched away to this some skinny region here. In principle, in the continuum, it's some delta function. Okay? And everything that was in here is scrunched away into some skinny region in there. Okay? All the other x's in this problem satisfy exactly the same Gauss's law wave equation as before, except that we're adding a delta function source that corresponds to the sum of all of these meshes that I scrunched away. Why? Because if I look at a Gauss's law for a little Gauss's pill box between here and there, I have this plus this minus that equals the sum of whatever these things were plus this scrunched away region, right? So after I scrunch it away, my pill box now looks like this. So I have this plus this minus that equals whatever I had before, and I have to account for whatever was in here. That's why I have to include that as a delta function source there, but it doesn't matter. It's just some other positive source, right? So what does that tell me? That tells me that every point on this space looks exactly the same as the point on this space. What does that look like? The direct product of two problems of exactly the same type. So this is manifest factorization. All right. Any questions about this? So maybe we can sum up. So we went to our kinematic space. We just labeled, the kinematic space was just obtained by labeling the variables, okay, looking at all the xij's. The interesting thing was that whether ijkl's cross or not was related to what looked like an emergent kind of causal structure in the 1 plus 1 dimensional space of the labels. Okay? In that 1 plus 1 dimensional space, we have all these x's, and we ask for these x's to satisfy the wave equation. What is that doing? That's identifying my kinematic space is n choose 2 minus n dimensional, right? Asking it to satisfy the wave equation is doing what? Is asking for it to lie on some plane in this nn minus 3 over 2 dimensional space. In fact, an n minus 3 dimensional plane in this high dimensional space. Okay? That n minus 3 dimensional plane is associated with the solutions of the wave equation. Once I do that, on that n minus 3 dimensional space, the positive region looks like the icosahedron. Right? And what is the scattering form? The scattering form is an n minus 3 form that lives on the whole kinematic space with the magic property that when you pull it back to the subspace that satisfies the wave equation, you get the canonical form for this icosahedron. That's the part which I have not proven to you yet, but which we saw the little example already at 4 points, right? Where we took dx13 over x13 minus dx24 over x24, and that combination is exactly fixed by the requirement that when you pull it back on the wave equation space, x13 plus x24 equals c, you get the form for the interval. Okay? This makes it manifest that the object is projectively invariant. Why? Because when you pull back onto these spaces, it should only have singularities on the icosahedron and not at infinity. Right? So that's projective invariance. And the fact that the singularities are polytopic and that they're captured by, and that they have a correct notion of locality and unitarity is an emergent property from the positivity. So if I draw the sort of big picture here again, so we have a big kinematic space. We have a big kinematic space. Here it's a space of all the xij. All right, and this is a giant space, so this is a big kinematic space. This is an n minus 3 over 2-dimensional space. In this space, first of all, there's a positive region where all the x's are positive. I should really draw it as an orthant, okay, but let me just draw it as a big ball. So just excuse my, this is a little impressionistic, okay? This is because I don't want to draw it infinite. So this is the space where the x's are all positive. So this is a big positive region P. But on top of that, there's a family of, not a unique one, they're labeled by the C's, right? But there's a family of hyperplanes. These are now n minus 3-dimensional spaces. These are determined by the wave equation, right? This is where x satisfies wave equation. With, again, they have their own notion of positivity, with C's positive. And the intersection of this n minus 3-dimensional family of planes with P is the icosahedron, right? The intersection is the icosahedron. Finally, what's the amplitude? The amplitude is an n minus 3 form in the nn minus 3 over 2-dimensional space. That's the amplitude form. It has the property that when omega is pulled back to any of these wave equation spaces, it becomes the canonical form for the icosahedron, which is revealed there. Okay? So that's sort of abstractly the question in kinematic space. I hope it's clear. There's no interior space-time, there's no virtual particles, there's no Hilbert space, right? The question is now purely posed in the space of the kinematic data. And this is what the answer looks like. It's a little weird, right? But this is the sort of flavor of things that, that we're going to get used to. What does this make obvious? The positivity makes locality, unitarity obvious, together with the polytopality, of course, which is an extra surprise, and the projective invariance. One way of computing this canonical form has a name that you know. It's called Feynman diagrams. Okay? And that is an interesting triangulation that you can do for a big class of polytopes. So let me just show you how it works in a simpler example. So what we're after then is we need to find the canonical form of these icosahedra. Well, we really need to lift it to something that lives in the whole space. But the interesting part is finding the canonical form of these icosahedra. So let me give you, let's actually start with imagine you had like a square like this. Okay? So let's say you wanted to find the canonical form of this little quadrilateral. Well, I told you a few ways of doing it, but one of them by triangulation. You do this, this triangle plus that triangle, or this triangle plus that triangle. Well, here's a nuttier thing that you could do. It seems a little bit nuttier at first, and then I'll tell you why it's reasonable from another point of view. Add an extra, but there's something funny about these. You see, if you do this, I'm adding an extra line that's not there in the problem. So that corresponds to a pole, which is not there in the answer. That's a spurious pole that then cancels in the sum. Okay? This is very, in the context of gluon amplitudes in n equals 4 super Yang-Mills and the amplituhedron, these are sort of triangulations of the amplituhedron that look like BCFW. They introduce spurious poles. Okay? Now, there's another kind of triangulation that you could do. Let me jump to the one that's relevant for us. Add an auxiliary line at infinity, or somewhere outside, right? And now you could do this really nutty triangulation. This this square is, you take every vertex and you continue the triangle that you make out of it, but with all anchored on this one extra line. Okay? So you take this vertex and you make this triangle. You take this vertex, you make this triangle. You take this vertex, you make that triangle. So how do you make this thing? Well, it's the big triangle minus this little triangle, minus that little triangle, add back in this tiniest triangle that you over-subtracted. Okay, so there's this inclusion-exclusion formula that you can give anchored on the vertices of the polytope. This actually, yeah. Yes. I'm basically done. Just 2 minutes. I just wanted to make this one point, and I'll stop. This guy, this works in any number of dimensions, so long as the polytope is what's known as simple, so that the number of facets that meet at any vertex is equal to the dimension of the space. Okay, that's true for the icosahedron. It's not true, for example, if you imagine a square pyramid. A square pyramid has 4 facets meeting at the top of the pyramid. So 4 is bigger than 3. It doesn't work for that, but for any simple polytope, it works. All right? What makes this not so crazy is if you imagine drawing the dual of this picture. If you draw the dual of this picture, each one of these vertices becomes a line, so you get another quadrilateral. But this line that's outside turns into a point that's inside. And this funny triangulation is just this way of decomposing the quadrilateral into 4 pizza slices in a natural way. Okay? So this is another thing that we've learned a lot in this business, is that you can have triangulations of an object and triangulations of the dual object. Natural triangulations of the object give you funny triangulations of the dual object and vice versa. But Feynman diagrams are a natural triangulation of the dual icosahedron. Okay, which corresponds to a term that you associate with every vertex. And remember, every vertex is one of the Feynman diagrams. Okay? So that's one universal way of triangulating the icosahedron. It's known as Feynman diagrams. Why does it break projective invariance? Because every term has a stupid singularity at infinity, which is not there in the problem. This totally artificial plane that you added from the outside. Okay? That cancels only in the entire sum. And so that means there are other ways of triangulating the icosahedron that are much more efficient than Feynman diagrams. Okay? And of course there are. And so there are ways. This is the analog, again, it's exactly the analog of BCFW triangulations of the amplituhedron have nothing to do with BCFW, but they're in the geometrically the same vein with the projective invariance playing the role of dual conformal invariance. There are triangulations of the icosahedron that manifest projective invariance term by term and are, of course, totally different. They don't look anything like Feynman diagrams, but they make some of the symmetries manifest. Okay? So this is the sort of character of the answer in this way of thinking about things. And just a final comment is that back in 2016, we had found a picture for the amplituhedron for n equals 4 super Yang-Mills. Not the original picture that we first ran into, but a different one, a somewhat deeper one, directly formulated, again, in the kinematical space. In that case, the kinematical space, Yara maybe mentioned, it was the momentum twister space. But the picture was exactly the same, 100% the same. Just the details of what the kinematic space was different. Instead of being the space of these xij's, it was momentum twistor space. Instead of being the x's positive, there was another positive region in the momentum twistor space. Instead of being these wave equation planes, there was another set of positive planes naturally formed to that problem. But everything, but the zeroth order structure, that you have a positive region, a family of planes that intersect them, revealing a positive geometry on the intersection, and the amplitude form being determined in this way, was common for both pictures. All right, so that's it for today. Tomorrow we'll come back and start from a different tack, as I say, a more systematic tack, but which will maybe at first, you'll wonder where it's going at first, but quickly I hope you'll see the point. The second tack will then immediately tell us how to do this for all loop orders. So this is a story at tree level, blah, 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 but there's a picture that now extends and connects to string theory in interesting ways, and maybe, I hope we'll have time to tomorrow to talk about some of this. All right, thanks a lot. You can also ask me over dinner, by the way, but yeah. Or after dinner, yeah. Go ahead, yeah. Oh yeah, sure, sure, yes, yes. This is the question, that's right, that's right, that's right. Oh, yes, 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 yes. No, we're not there yet. That's right. Yeah, that's right. Yeah. It's not. But tomorrow we'll talk about integrated amplitudes. So tomorrow we're really going to be talking about amplitudes. No. Well, this is first of all just at tree level, so there's no loops or anything like that in this picture. Now, in this whole subject for a long time, there's been an aspect that had to do with integrands, and then you had to learn to integrate. Okay. Tomorrow we'll be talking about essentially a dual of this picture. In this dual picture, though, there has certain advantages, and one of them is that we'll be able to integrate. And we're really going to be talking about actual amplitudes tomorrow. Okay? Full amplitudes.
Well, I'm looking forward to it.
Yeah.